on variation in height and seep location of methane plumes in the Gulf of Mexico. So this is the exploration vessel Nautilus. It's actually the same ship that discovered the Titanic. So it has an ROV that is neutrally buoyant, so we can go down and survey the floor. And also has onboard multi-beam mapping, so we can look at the seafloor, which is what I utilized. Our expedition route was we started at Gulfport, Mississippi, and then went down to the bottom left where you can see GC 600, confetti plume. However, there were strong surface currents, so we couldn't actually maintain position. So we had to end up going to MC 118 or Sleeping Dragon, and that's where we were able to conduct 4 days of surveying this year, and last year they conducted 3 days. So the motivation is primarily that these seeps are under study. We know they exist, we know they emit methane, we don't know how much, we don't know how reliable they are, we don't even know their flux rates. There's also an abundance of chemosynthetic microbial life, which actually played a large role in helping get rid of the oil from the Deepwater Horizon spill. How much oil they got rid of, how fast they were able to even metabolize it, we still don't know. Then the last 2 points are actually connected, is that the methane is actually bubbling up through the seafloor, dissolving, and eventually may actually reach the surface. The bottom of the sea is actually separated on timescales of about 50 years from the surface. But when we were driving around, or sailing on the surface, our chemistry team actually detected high concentrations of methane at the surface, where we technically shouldn't have seen anything. And so if this methane is actually getting up to the surface, it's being released into the atmosphere, and people who investigate global warming would care about these things. So a seep is basically where hydrocarbons like oil, methane, propane, butane leak up from the seafloor. Where these plumes interact with the water, there is actually dissolved methane that reacts with the methane that's coming out and forms a carbonate, a hard rock, which can plug up the seeps. So you have methanes come out for a little bit, it plugs and gets moved. It can also build up pressure. And so there are times with the ROV when we went underwater, we're on our way down, and the seafloor just explodes. And then because the methane has saturated the rock actually flips up. So it's very pretty. So this here is a sleeping dragon. It should play. You can see right here that there's tiny little bubbles, right? It's going to be easier to see, but you could miss these if you were 2 meters to the side. You can see this is carbonate, and there are tiny little bubbles that are bubbling up. There's also some obligatory biology. We also saw a whale.
That's really cool biology.
Yeah.
Except for the small fish. They got eaten.
Yeah. The physics behind my research is actually fairly simple. Sound waves travel through water and reflect off obstructions. Problem is that if you do this to a seafloor, you pick up all the seafloor. So the first thing we do in a multi-beam is we narrow the beam to only pick up a certain amount of the ground. You put them together, and there are multiple beams. This is multi-beam, 129 actually, and then map the seafloor. This is useful for us because bubbles are actually detected because of resonance due to standing waves. When an acoustic pulse hits them, certain size bubbles resonate at different frequencies. It sets up a standing wave and actually allows them to reflect more. And so because of this, we can actually see something that's very distinctly not noise in our water column.
What are the wavelengths of these waves?
Wavelengths can go from, I don't know the wavelength of these multi-beam waves. I had a professor who's doing things from 30 kilohertz to 500 kilohertz, I think, and would take 4 data points and actually use that to plot the bubble size distribution.
How big is a typical bubble?
A typical bubble can be anywhere from a few millimeters to slightly bigger. It's complicated by the fact that they actually get a hydrate coating that interacts with the surface of it.
Also, is there a bubble size function depth? Do you have to be tuned to
The bubble size will actually increase as it goes up because of the change in pressure, but then it actually dissolves in the water, so it is roughly uniform.
Okay, we'll remember to hold questions till the end. We'll grade Ben for 2 minutes, and then we'll chat with him for an hour.
We actually used the multi-beam by simply following a grid pattern. Whenever you turned, as it's a periodic thing, you would get holes in your data. So you would just sail around for 10 to 30 minutes, turn it off, turn around, and go back again. We then stitch them back together and sum them up. These are very diffuse plumes and they're hard to see, so summing them like this actually gives us a real concrete object to interact. We visualize the program using Fledermaus, which is German for bat, because sonar, and then we're able to use georeferencing tools to actually determine where they were and the seep sites. Yes, okay. No? Pressed it one more time. Yep. There we go. That should be the right number of times. Great.
I think,
All right, moving on to results.
actually, if you hit escape, you can pick this page directly,
Unless you crashed it.
unless you pressed it.
Computer may be frozen.
Oh, we picked it. All right. So this is a picture of the multi-beam. You can see the sonar fan. This one's actually 5 kilometers total across. Because of the one we were using in the depth, there was actually about 1 kilometer on either side. You can see that there are different colors that add up together because you have multiple passes. Each pass is registered with the color and then gets stacked together. And so you can really see where these plumes are on the seafloor. So the results, first off, is that seeps move. This is the most striking way I can demonstrate this. You have the 14th of April on the left and the 18th of April on the right. The first thing you notice is that there were 3 plumes in one picture and only 2 plumes in the other picture. So we have methane that's bubbling up out of hydrocarbon reservoirs, just fiercely, just as strong as the others, that just gets plugged. And more importantly, it doesn't go somewhere else, it just disappears. And then the following day, the plume actually came back. And we've observed this both this year and on the cruise for last year. Secondly, you can actually see that our multi-beam can actually resolve 2 plumes here. They're very close to each other, and they mix together as they go up and are bent by the current. But you can definitely see that there are 2 plumes. So it isn't that there's just one specific site. It can be one location, and they can be moving within that location. So, crash again? No, good. So this is the primary results, because what we care most about is the actual variation on the seafloor. This is a map of the bathymetry mapped with different colors representing a plume site. So you can see that they're all over the place. It isn't that there's one place that's pouring out plumes, it's anywhere. So we just simply said, okay, we're going to divide this into 1 plume, 2 plume, 3 plumes, and look at it that way. And so we get a standard deviation for the plume sites, for 2 of them being roughly about 40 meters in the X and Y direction. So they actually are moving around quite a bit. The plume 3 site up there, you actually have much higher standard deviations. And that's because in these you have very strong plumes that are able to, we map them by taking the lower points that we see that are below the currents and just projecting them onto the seafloor. And we can average those. That, you actually have a whole bunch of plumes that aren't plumes that you would identify, but they are bubbles from possibly fish or other items. And because they are so much less strong plumes, much weaker plumes, they are able to bring in more noise. And so the next step of the MATLAB code is to actually average out the positions and then go back and get rid of the data that doesn't belong to those average positions. So as of right now, we just average positions below a certain point. We can do that and then go back and get rid of outliers that way. Like this little guy, we got rid of him by hand. So continuing more, you can see this picture of plumes here. There are a whole bunch of plumes everywhere. And so we want to be able to look at smaller resolutions. We want to be able to pick out each of these plumes and plot all of them. We want to be able to characterize diffuse plumes. You can have the sleeping dragon that I showed you was actually a video from last year, where that sleeping dragon was all the plume. It was glorious. You could put a backplate behind it and cameras and measure the flux, and it was beautiful. And you went down there, and people were just disappointed because it wasn't active at all. 10 meters to the north, there was just a giant flatbed that would have bubbles randomly popping out of it. So it transitioned from going from a very definite source to a diffuse one, and we want to be able to characterize that. I'm working with several doctors to integrate this with the acoustic data, which took 4 different frequencies, so we could get bubble size throughout the columns. There's chemistry, which can actually talk about the amount of dissolved methane at every level, so you can figure out how much of the bubbles are leaving. and then optical data that actually helped watch the bubbles as they moved, and also another way to calculate their velocity, and actually help really characterize this plume using BP's science settlement money. Any questions?
So where does the XY resolution come from? So you have
The
this
XY
multi-beam.
resolution comes from the multi-beam.
And how? Like, how's it doing that?
So you have 129 transponders that all just shoot down, and they each have their own resolution that they can determine
But
things
these are
with.
just an array of transponders that are shooting down? or
Imagine it like a
separate?
fan.
Okay.
And so that fan, you project onto each point, and there's 129 of them. And so we're good at acoustics, and we can actually,
But where are the transponders located?
on the boat.
Okay, so they're up on the top, and you're shining the ultrasound down,
Yep.
and it bounces off the stuff that comes back.
Yep.
Why isn't it mishmash that I don't know? where it
Because they're narrow beam. So in the
So they're
beginning,
really narrow.
And you only fire one of the 190 at once?
I'm sure that the technology manages itself, right? I know that, I
Okay.
think it's, you send it and it'll come back at a certain angle, and it'll, because if they're directionally oriented, they won't pick up something coming
Okay,
from another
so they
side.
are pretty, they actually have pretty good spatial
Also,
resolution. What's that resolution, like how big is?
These resolutions might be about 5-10 meters, which, given the seafloor, is actually pretty good.
How do you make a narrow sonic beam?
All I know is that the narrower you want it, the bigger it has to get. You have things that focus it and make sure it's in one direction. I don't actually know the technology.
Called diffraction.
Yeah.
Is that scaling or just 10 or 12 fixed beams?
They are fixed. You have 129 fixed ones. They like compensate for the roll of the ship and the motion, and they manage to do all that and still get a lovely picture of the seafloor.
What
So
is
you're
the typical-
quoting standard deviations of 50 meters to the nearest centimeter. Does that make any sense?
Those were, no, probably not.
So, I mean, when you, for me, standard deviation is the spread in the numbers you're getting back.
So when we do the bathymetry, we actually used a resolution of 10 meters because that's what my advisor / mentor gave me. I can actually later, when I write the paper on this, can go and actually find the resolution of the multi-beam. Because we were picking up different plume sites from sites that are actually like not all that far separated. Yes, centimeters is a
Yeah,
little.
it seems like
over
you
the top.
are resolving that, so I don't quite understand what that standard deviation number you're quoting is.
So what that comes from is, it comes from I take the bottom 750, I take the points that we detect below 750 meters, because these aren't affected by a whole bunch of currents. I then project those down to the seafloor, and then average them to find a mean point. And so at that point, I compare and find the standard deviation between these points for a given plume.
This is almost mapping like a random walk of seeps, right?
Yep.
Is that the idea, that the standard deviation is characterizing how the seep is moving?
Yes, it characterizes that if we identify a seep, how likely it is to move.
Can I ask a question? When you calculate the standard deviation, this is over the course of your 4 days?
7 days, because I got 3 days from last year.
Okay, so 7 days measured once per day.
Which is kind of alarming that is the most accurate or repeated study that's been done. There are approximately 2 papers talking about methane plumes in the Gulf. There's one talking about them in a lake, and they are all looking at the plumes once over. This is the first time anyone has actually gone to a site over multiple years and just looked at it, because that's how understudied they are.
Is there a sense as to what the total volume of methane is, which is evolving out of these beds? Is that where all the methane comes from that's in the air?
So last year, when all the methane was coming out of that one spot, Sleeping Dragon, they could actually estimate a flow rate and get something that was reasonable and look at it. Here, we weren't able to do that immediately. Once we get all the data together, because there are multiple plumes, we did a whole bunch of transits. We had an ROV for 12 hours, down for 12 hours every day. We might be able to actually get that. But that question you asked, no one knows the answer to, which is why we're there.
How much of the methane gets to the surface?
No bubbles of methane reach the surface. Bubbles of oil reach the surface. Most of the methane has completely dissolved by about 450 meters depth for the largest biggest plume. However, there's a caveat to that, in that our chemistry team, while we were doing those grids, was sampling the seawater every 5 seconds. And they got hot spots of dissolved concentrations of methane directly over where the currents from the plumes would have gone. So the bottom of the ocean and the top of the ocean are supposed to be separated by timescales of 50 years. But if we're getting hot spots on the surface that correspond to the plumes plus currents, that means we have methane that is going from the seafloor at least to the surface, where it can then become steady state and leave the water.
Where'd you get that 50-year number?
Oceanographers.
How deep is it?
The Deepwater Horizon site is about 1,000 meters deep.
Why are you in doubt or concerned about how methane would be produced on the top of that oil field? It seems like methane is sort of a given out of that area, isn't it?
Well, so you can assume that methane's given out of the area, but like there's a whole bunch of rock that's been pressing down. Like, yes, there's methane, but how much methane? Where is it coming out? These are questions that if we don't have the answer to, we're scientists and we want to go find it out. It was made, right, we got $300 million from BP after they did the Deepwater Horizon site, right, which, complete side note, the ROV actually went to examine that wellhead and it's not leaking.